Part A, Problem A3. A certain planet of radius big R is composed of a uniform material that, through radioactive decay, generates net power big P. This results in a temperature difference between the inside and outside of the planet as heat is transferred from the interior to the surface. The rate of heat transfer is governed by the thermal conductivity. The thermal conductivity of a material is measured of how quickly heat flows through that material in response to a temperature gradient. Specifically, consider a thin slab of material of area A and thickness delta x, where one surface is hotter than the other by an amount of delta big T, delta temperature. Suppose that an amount of heat, delta Q, flows from the slab in a time delta T. The thermal conductivity K of the material is then K equal delta Q over delta T multiplied by 1 over A area and multiplied by dx over dt. It is found that K is approximately constant for many materials. Assume that it is a constant for the planet. For the following, assume that the planet is in a steady state. Temperature might depend on position, but does not depend on time. So, first question. Find an expression for the temperature of the surface of the planet assuming black body radiation and a emissivity of 1 and no radiation incident on the planet surface. You may express your answer in terms of any of the following variables and the Stefan-Boltzmann constant sigma. Question B. Find an expression for the temperature difference between the surface of the planet and the center of the planet. You may express your answer in terms of any of the above variables. You do not need to answer part A to be able to answer this part. Question A. Find an expression for the temperature of the surface of the planet assuming black body radiation. According to formula Boltzmann, we have power proportional to temperature power 4, this one, where sigma is Boltzmann constant and A it's area and T is temperature, absolute temperature. And now from this formula we can immediately find what is the temperature of this planet. This is the expression. We have 4 pi r squared, that's the area on the surface of this planet. And this is the answer for question A. Question B. Find an expression for the temperature difference between the surface of the planet and the center of the planet. Now let's assume that delta Q over delta T, it's a radiation created in any part of planet with the same density. So it means that radiation proportional to volume. If we take a sphere of radius small r, we can count what is radiation created by this small sphere, and it's proportional to r cube. So it means that we know what is dq over dt, and we can put it here. And also we know what is area of this small sphere, and we can rewrite this formula in form of, and after splitting variables we have this formula delta t delta temperature equal power over 4 pi k big R cube multiplied by R dr. And after integration we can find what is a temperature difference. That will be this one. On the left side we have temperature difference, and on the right side we integrate from 0 to big R. So that's the answer for question B.